All right, thanks everyone who's come. There's a lot of material in these slides, so I'm just going to go ahead and jump right in it. I would recommend to double click the slide deck to make it bigger because there's code on the slide deck and a lot of things reference the slides. I'm Richard Rhoda. I'm a senior technical lead at Perspecta with over 15 years of Java development experience. I'm Oracle Certified Professional Java 8. And at parts of this presentation, I'll tell you things that I've seen on the exam if you're studying for the 8 or beyond. And my LinkedIn and Twitter are here. And if you want to follow along, you can obtain these slides in PDF form at that link. What is a Lambda expression? A Lambda is an unnamed function object. Member of a class where a Lambda is declared and arguments and local variables that are effectively final may be referenced by a Lambda. In Java, a Lambda must be assigned to a functional interface. Effectively final means that you can take a local variable or argument and add the keyword final without breaking compilation. It is effectively final. The compiler infers that the variable is final even if it's not declared as such. There's no such requirement on the class variables. The dash greater than is not a typo in these examples. The Lambda operator is equal greater than in most other languages, but Oracle, even though Java was one of the very last languages to support Lambda, decided to be different and use dash greater than. In their documentation, they suggest that programmers might get equal greater than confused with greater than and equal. When I've programmed JavaScript with arrow functions, I've never ever gotten those confused, and that doesn't actually happen, but here we are. Example 1a is a predicate that returns true when it's given or tests the value 5. Example 1b is a higher order function that returns a lambda that's true when given a value matching the value passed into the higher order function. What a higher order function is a function that either takes a function, returns a function, or both takes and returns a function. In the var declarations below, the first var declaration does not work because there's no functional interface. The compiler has no idea what to do with that lambda. But the second var declaration does work because the make test func returns a predicate which implicitly becomes the var predicate type. A lambda may have a single statement or a statement block with a return. Unlike other programming languages, the value of a Java Lambda is not implicitly the last expression executed. The return value is necessary unless a single statement form is used or the return type of the Lambda functional interface is void. Only a single argument is valid without parentheses, but any argument list is always valid with them, including the single argument. The argument type names in the examples below can be useful to resolve ambiguous Lambda expressions. These can occur when a Lambda is passed to an overloaded method with multiple FIs and more than one match, but they can be distinguished by their type variables or by their actual declaration. A functional interface. A functional interface contains exactly one abstract method called the functional method. Default and static methods are not abstract because they define a body, and also static is technically not part of the interface anyway. Equals and hash code are not abstract because they're defined in objects, so anything that's implicitly defined in object can be in a functional interface without making it not a functional interface. The optional @functional interface annotation causes the compiler to verify and enforce that there is exactly one abstract method. If you take the OCP exam, you will see something similar to this. This illustrates the difference in using a Lambda expression versus an anonymous inner class. Note that the Lambda expression is 8 characters in a single line. Java 8 uses type inference from the functional interface to produce a Lambda with the correct return value and arguments. This saves much code. Notice how much more readable the Lambda is than the inner class. Java 8 also optimizes Lambda. Since that Lambda does not reference any outside variables or outside code, Java 8 will automatically create a single constant instance of it and reuse it. With the inner class, because it's explicitly declared with the new, Java has no choice but to create a new instance each time it's called. This introduces the key functional interfaces defined in Java 8. These are used by the Stream framework, and not to be confused with IOStream. They are completely unrelated. You really need to know these cold if you are going to take the OCP exam. These conventions are consistently used by the Java functional interface. T is the first argument and sometimes used as a return value if there's only one type. U is a second argument for functional interfaces that have one, and R is a return value. If any of these are omitted, or they are not used. And many, not all, but many FIs that take one argument have a corresponding two-argument version prefixed with by. The predicate is one of the simpler functional interfaces. This is if you are taking the OCA, the Oracle Certified Associate exam, this will be the only built-in functional interface on that test. It's used for true, false, yes, no type answers. The Stream framework uses predicates to find a matching element or filter the stream to only contain matching elements. The related primitive FIs are like their generic counterparts, except that they accept a primitive value of double, int, or long. Other related primitive FIs, depending on the context, also return primitive values. The consumer is typically used to do something with a value. The for each method may be used as a replacement for the imperative for loop in many cases. This Lambda can also be used to implement a form of the visitor pattern. Instead of needing a constellation, just a whole bunch of classes to implement the various collection visitors, the consumer FI and for each method can do the job instead. And the reason I said a variation with visitor, you would probably more properly call this a visitor-iterator pattern, because the visitor pattern has both the iteration and what you do in the visitor, and these visitors merely act on it while using the underlying iterator of the container. The supplier is typically used to create something or provide a value. However, there is nothing in the semantics of the interface that requires the supplier to create a new value. If code does expect a new or exclusive value from a supplier, it should be documented. The supplier may also be used for pattern-based developments. Instead of needing a whole constellation of classes to implement the factory object pattern, the supplier FI with lambdas can do the job instead. And it has related a double, int, and long supplier for the primitives. Function accepts a value and returns a result, and is commonly used to compute a result or map one value to another. And there's a whole zoo of related primitive FIs because all the combinations of going from one primitive to another are supported, and it has a two-argument version. The function as mapping idea is used extensively in the Stream framework. The operators are specializations of functions and bifunctions that require the turn type and all the argument types to be identical. Unlike functions, they do not follow the by convention to distinguish the 1 and 2 operator versions. Instead, there is a unary operator that takes a single argument and the binary operator that takes two arguments. And since it requires all the types to be the same, the related perimeter functional interfaces are a lot more tame because you can't be mapping one to another. The comparator accepts two arguments and returns an integer to impose a total ordering or sorting on a collection of objects. And you're probably familiar with this interface if you've done any Java development because it's been around since the early days of Java. However, it's worth a mention here because it has a role in sorting data in the stream framework. The stream framework avoids returning null values. Instead, it returns this optional container class for operations where a value might not exist. This typically happens when a stream is empty. However, it can also happen if a stream fails to find a requested value as well. It has a isPresent to query if a value exists, ifPresent, which executes a consumer, which does something to a value when the value exists, and various get methods that obtain the value if it exists or perform another action if the value doesn't exist, such as return a substitute value, which could be null, or throw an exception. In the first example below, this introduces a method reference. A system out : println is a method reference, which is a shorthand way of writing a Lambda that calls a single method. And that brings us to method references. The method reference is a shorthand way of specifying a Lambda that only calls a single method. The specification also guarantees that method references are folded into a single instance at runtime. However, as a practical matter, any Lambda that doesn't use anything except the arguments that are passed into it will also get folded into a single instance. And there are various types of references, and once you're familiar with the syntax, these can often be read and understand faster. And you can always take a method reference and transform it into a quote-unquote longhand Lambda, but a longhand Lambda cannot necessarily be transformed back into a method reference. Perhaps the most straightforward method reference to understand is the static method reference. The static method is bound to the functional interface with the arguments in the static method bound in the same order they occur in the functional interface. So here you see public static value of an array of characters on the string class. And that's being bound to this function class that takes the array of characters and returns a string. So when the string functional method apply is called, it dutifully spits out hello. A method reference on an instance is very similar to the static method reference, except that it is bound to a specific instance of an object. An instance is only eligible to be used for a method reference if it is a class member, an effectively final argument, or an effectively final local variable. As in the case with the static binding, the arguments are bound to it in the same way in the order they are declared. Recall that the for each method on a collection is that processes each element with the consumer. So here we have a print method on print writer that's bounded to this printer, and then the arrays as list is sent to the printer, which outputs 1, 2, 3, 4. A constructor method reference is used to create new instances using the specified constructor. They may only be bound to functional interfaces with a compatible return type. And I say here that supplier is canonically used for constructor method reference. And what I mean by that is, since the supplier's sole purpose is to supply a value, it is the most natural of the Java FIs to select for a constructor. The supplier requires a public constructor with no arguments in order to be bound using a constructor method reference. On the OCP exam, anything, and I mean just about anything that asks which FI to use for a Lambda involving a constructor, the right answer is always the supplier. Recall that the urinary operator is a specialized function that returns the same type of its argument. The instance method reference may be the most difficult to understand. Although this reference is named against the class, it is applied to an instance of the class by using the first argument of the Lambda as the object instance to apply the method to. Any remaining arguments in the FIs are bound to the method arguments in the order they occur. The first argument rule has significance with the bifunctional interfaces because only the class type of the first argument may be bound as an instant method reference. In this case, we have toUpperCase, which requires a string instance. We bind it to the urinary operator, and that gets transformed to s.toUpperCase. So as each string is submitted to the apply, its toUpperCase method is called, resulting in the uppercase ABC. Stream. They're like monads, and they have nothing to do with I/O streams. If you are familiar with monads in functional programming, the Java stream shares many similarities with them. If you Google this, there's a debate if Java streams are really monads. And for getting work done, it really doesn't matter. If you're familiar with monads, you should feel right at home with streams. The Java stream framework has nothing to do with I/O streams. The key difference between a stream and a collection is a structure to store data. A stream is a structure to perform a computation. A stream is passive until a terminal operation is run. A stream consists of a data source, which provides the values for processing, 0 or more intermediate operations that transform or discard values, and the intermediate operations are lazy and only executed when a terminal operation is added, and a terminal operation returns a result or processes the stream elements. The terminal operation is eager, and it's what initiates the processing of the stream. Once a terminal operation is applied, no other operations or changes may be made to the stream, and any further operations result in an exception. Streams are kind of like factory conveyor belts. The data source, that's the raw material you're processing. That's what's coming in the factory door. Then adding the intermediate operations is like getting the workers into place. And the terminal operation can be thought of as the worker who packages the finished product. And like a conveyor belt takes the result of the previous worker's changes to the next worker, a stream takes the data source output of the previous intermediate operation result as the input to the next intermediate operation or the terminal operation. A conveyor belt doesn't start until all the workers are in place and ready. Likewise, a stream doesn't start until all the intermediate operations and the terminal operation has been defined. Defining the terminal operation starts the processing. Once it is running, it can't be changed. That can't be emphasized too many times because in the OCP exam, they will try to give you a stream and they do an operation after the final one. It's all over the test. Consumers typically, this is an example of reduction to add a collection of numbers. A reduction computes an operation by processing every value in the stream. Given this collection of numbers that has integers from 1 to 1,000, add the collection. And you have the example of how to do that as a for loop. And the stream reduction uses a binary operator, and it uses a lambda that takes I, which is a current element, and a sum, which is an accumulator, which sums all the values. And one important thing to note about the I, sum lambda is it is a pure function because it only reads its arguments, does not change any external state, has no side effects, and always returns the same value for the same two arguments. For example, if you apply 3 and 4, the result will always be 7. Pure functions are inherently thread safe and should be used with streams whenever are possible. Otherwise, a non-deterministic and unpredictable behavior may occur. Consumers or suppliers are notable exceptions to this rule. And here's why they are notable exceptions. Consumers typically do something with a value such as print it to an external source. Given the rules about pure functions, only a consumer that does nothing is a pure function. Since that's not useful, consumers are generally never pure functions. Suppliers that create a new instance with each call are not pure functions because they return a different value for the same void argument, but suppliers that return a constant value are pure functions. I will say this, though. A supplier that internally creates a new instance is generally thread safe because each thread is executing and getting an independent instance of all the other ones. To break down this previous stream, all streams have a data source, and this one's the numbers. Numbers reduces a terminal reduction on the stream. The reduction processes all of the values to a single value. Other integer reduction examples are sum, average, median, min, and max. The first argument to reduce is the identity property. For addition and counting, it is 0. For multiplication, it is 1, and for strings, it is the empty string. The lambda is a binary operator that is given a running total and the current element. They're processed by adding them together. And in mathematics, an identity property is a number or value such that when it is applied with an operator, it does not change the value of the other operand. So 0 plus x equals x, 1 times x equals x, empty string plus x string is x string, etc. The identity property is passed as a second argument to the binary operator the first time it is called, and it is also what is returned if the stream is empty. So streams that start with identity property are never optional. They always return an actual value. The primitive streams are int stream, long stream, and double stream. They offer a significant performance benefit over the generic stream by avoiding boxing and unboxing of their primitive computations. They offer additional built-in terminal operations such as sum, min, max, average, and summary statistics. Although each of those operations could be done with a reduce function, it's nice to have them built in. They can replace a traditional for loop with a range and for each. In this example, this is a loop from 0 to 9. There's also a range close that would print from 0 to 10. You can use map to int, map to long, map to double, and map to object to convert an existing stream to an int stream, long stream, double stream, and stream respectively. You can use the box method to convert a primitive stream to its corresponding object stream by boxing the primitive values. Intermediate operations. These create a new stream with the operator appended to it. Map should not be confused with Java util map. This is the idea that functions can map input values to output values. A pure function should be used as possible. They may change the element type of a stream by returning out values of a different type. Here I have an example where I start with an integer stream of range of 65 to 75 non-inclusive, but I map it to characters. So the resulting stream is actually a stream of characters, which of course prints the letters A through J. I can also change the values but keep the data type by using map and making a function that returns the same type. In this case, I multiply the values by 10. The map is, of course, a reference to the mathematical concept. Any function may be thought of as a means to mapping its input values to the output values. The map to object lambda is a pure function because it returns its integer argument as a character. In all of these examples, it is the terminal operation for each stream that produces the output. Until that is called, the stream is passively waiting for more intermediate operations or the terminal operation. The filter intermediate operation creates a new stream with the contents of the previous stream where the predicate or primitive predicate is true. This filter allows integers that are divisible by 4 to pass through. The other integers are discarded from the stream. The output of the summary statistics shows a count of 250, which is how many integers there are that are evenly divisible by 4 between 0 and 999. The instream.range method includes the starting number but excludes the ending number. There is an instream range close method that does include the beginning and end of the range. Limit and skip can be used on finite streams, but they are more associated with infinite streams because of their role in turning an infinite stream into a finite stream. The limit limits the values produced by a stream. The skip intermediate operation skips specified elements, and the order of these operations matters greatly. If you use skip before limit, the skipped items are not counted against the limit. But if you use skip after limit, the skipped items are counted against the limit. So when skip is used first, 6 items are returned, but when skip is used second, only 2 items. The State Iterate is a way to create an infinite stream by using an initial value with a unary operator to create an infinite stream. And if you're studying to take the OCP exam, you will see the skip limit or limit skip on that exam. Terminal operations. Let's get the party started in the stream processing. Some examples of terminal operations are count, which is a reduction that returns a number of elements in the stream. Never use it on an infinite stream. Reduce. Perform a reduction of the stream using a binary operator to accumulate the elements. Never use that on an infinite stream either. Any match. Returns true and stops processing if any element matches a supplied predicate, false otherwise. An empty stream is false. All match. Returns false and stops processing if any element does not match the supplied predicate. True otherwise. Empty stream is true. None match. Returns false and stops processing if any element matches a supplied predicate. Empty stream is true. For each. Avoid operation that presents each element to the consumer for processing. The match family of operations is not considered a reduction because it doesn't always process all of the elements. Although for each processes all the values and all the elements, it isn't considered a reduction because it does not return a value. By definition, reductions process all the elements, so never use a reduction on the infinite stream. And yes, that will also be on the OCP exam. These terminal operations return optional because the value does not exist in an empty stream. The value may also not exist if nothing in the stream matches what is asked for. Find first produces the first element in a stream. Because this implies ordering of the elements, any parallel stream is transformed into a sequential stream to guarantee element and counter order. Find any will produce any element on the stream. It does not impose any overhead on a parallel stream, but it may produce differing values on invocation of the same stream. Min produces the minimum element, and max produces the maximum element. The collector. All right, if you're into functional programming, this is heresy, but this is what Java does. It's a mutable reduction that creates an object to process all the stream elements. And of course, you should never use this on an infinite stream since it is a reduction. The collections collectors provide pre-packaged collectors to create a list or set. It also provides a to-collection collector, which allows the use of a supplier to create the collection to use. In this example, the collections to-collection uses a constructor reference to linked hash set to create a set that only allows one copy of each element and also retains a sort ordering imposed by the sorted intermediate option. The collector's collection is useful to leverage to give custom implementations of the collections with properties like that. The partition collector uses a predicate to create a map with the keys false and true. Both false and true key and values always exist in the map, even if the corresponding value is not present. In such a case, the value will either be an empty collection, an empty optional, or some account of 0, depending on the particulars of how the partition is created. Using the predicate in the previous example to create a map with elements divisible by 4 and not divisible by 4. So you end up with 3,075,000 that are divisible by 4 and 124,500 that are not. The summing int collectors that is used is an example of a downstream collector. In this case, it accepts the values from the partitioning by collector and produces a sum reduction of those values. By using collectors and downstream collectors, you can have some pretty powerful description of data That would have taken a whole lot of code without Lambda, with just a few quick lines of Lambda code. This example groups the words by their starting letter, listing each word with their letter. But in another twist, we use a tree map and a tree set to further demonstrate the flexibility offered by specifying the collection implementation. With very little effort on our part, we have produced a sorted map with a sorted set of values for each letter. The stream, and for those who aren't familiar, the stream of is a way to create a stream with specific values listed in the stream of. This is a rewrite of the previous grouping by to work with concurrent processing. Note that we had to switch out the tree map and tree set with concurrent skip list versions to support the concurrent processing. We also have a version using a downstream collector to count the number of occurrences of each word. There's a caveat. This is not necessarily faster than the sequential stream. In fact, it is likely this version is slower because the concurrent skip lists and map introduce their own overhead. It would be more appropriate to use a concurrency for values that take significant processing resources to compute, where the resources to compute the values are significantly more than the additional resources to store them. Joining collector. This is a process where a stream of character sequence can be concatenated together to form a string. And recall the About Jack stream below. This joins it into words separated with the space, and you can see all work and no play makes Jack a dull boy, but all play and no work makes Jack a fool. The argument to a collector's joining is the character to separate each part of the string. In this particular case, it's a space, but other characters such as a comma, think class path, semicolon, think Windows path, and colon, think of Unix path, can also be used. This is actually very handy when you have to delimit a string. Does anyone have any questions of what's been presented so far? All right, I will proceed with the auto-closable Lambda. These allow you to use try with resources with any class, and you can catch the close exception, among other magical things that they do. This is a functional interface that the Java books fail to mention. The auto-closable is a functional interface because it has a single functional method, void close, and the missing @functional interface annotation is none necessary. It's still a functional interface, even though when you look in the Java library, it's not annotated as such. So what? What does that mean? Well, in Java 7, try with resources was added to the language, but unfortunately, not every class that could benefit from it implemented it. But using lambdas, that doesn't matter. Anything can leverage try with resources. In this example, I have a context, which is common when you connect to an LDAP server. And I use a try with resources to close the context by binding the auto-closable to the context close method. But there are some issues. The close method throws exceptions. The thrown exception will either need to be caught or processed or redeclared in the throws clause, and it will kind of become a nuisance because you'll have the code being littered with unnecessary catch and throw statements. So you can fix this. You can derive your own auto-closable interface that throws the exceptions you want. However, this way of fixing it also has an issue, because now you have to create a new interface every single time you have a different exception or combination of exceptions that are needed in the throws clause, and people will forget that interfaces were created and create other interfaces that throw the same exception, and your code base will likely become a mess after any period of time. So to fix that, you can parameterize the auto-close exceptions. You can use a generic, and as long as you make close a default method and then delegate it to a different method, you can have a generic one where you can tell the compiler what exception can be thrown. I don't know why, but when you made the close exception itself parameterized and still abstract, the compiler had some kind of weird error when you used it with a try with resources clause, but when you do it this way, it works just fine. So now we can use a parameterized functional interface. We'll go back to the first example. The close method of the context forms a Lambda with a close at one interface. And the try with resources feature in Java does the rest, including all the heavy lifting of any exception thrown in the close method is either suppressed exception if it occurs in the body or its own first class exception if no exception occurs in the body. You can look here that close at one is parameterized with naming exception, and our use context method only throws naming exception. It no longer needs to throw exception. The decorator pattern was one of the core patterns introduced in the design patterns element of reusable object-oriented software by Gamma, Helm, Johnson, and Felicities. This pattern allows behavior to be added to an object dynamically by decorating it or wrapping it with another object of the same abstract type, such as an interface. This pattern may be leveraged to add capabilities to auto-closables, such as exception handling. Since auto-closable is a functional interface, the decorator may be expressed as a Lambda. In this case, we decorate the Lambda using a higher order function called wrapped_all_exception. It returns a Lambda that calls the close method of the original auto-closable, but if it throws an exception, it catches it and wraps or decorates it with a not closed exception. Actually, the not closed exception is better. It's better to call that an adapter than decorating, because you're decorating an unwanted checked exception with a much more easy to handle runtime exception. The closed Lambda is decorated to wrap the exception within the not closed exception. And here's the cool part. If you get an exception that only happens in the close method, you can handle it and catch it independently of when an exception happens in the body of the try catch. And before these decorators in Lambda, that was not possible to do. So the first time I introduced this, I was inundated with questions about it. So what I did is I have a project called Close It, and the coordinates of it to get it from Maven Central will be on the final slide. It supports 0 to 5 checked exceptions, and you've probably guessed it's Close It 0 is no checked exception, and Close It 5 is 5 checked exceptions, and everything in between. It makes it easy to use a try with resources, and the best part is you can completely replace the try finally construct. I've probably not written a try finally clause in probably going on 2 years because the construct is buggy. If you have an exception return in the finally clause and you let it go, then you've lost an exception that could have happened in the try clause. Or if you don't have an exception in the finally clause, that's pretty much the only time you're okay. So this project provides these decorators for handling closed exceptions. Ignore is when you pretend the exception never happened and you just discard it. Consume, think of the consumer functional interface. You do something such as log the exception, then discard. Rethrow is exactly like consume, except you then throw the exception. Hide hides the checked exception from the compiler. What I mean by that is the checked exception remains a checked exception, but the compiler doesn't see it, so you don't have to put it in your throws clause. And I recommend thinking long and hard before using that one, because you are breaking the semantics of the Java programming language, and you might not be able to guarantee if code will handle that correctly. And wrap will wrap the exception within another exception of a different type. And this is a form of the adapter design pattern. And this is what the previous examples showed. So here I have some links to Oracle's Lambda Quick Start tutorial, which is worth reading. these slides, the Close It project on GitHub, which explains all of that in even more excruciating detail, is pretty much everything you wanted to know about using auto closables and try with resources, but we're scared to ask. And there's also a project with some example code on GitHub. And you have my LinkedIn, my Twitter, and these slides. And now the floor is open for questions. Yes, it is. If you look at a monad and look at a stream, you'll basically say, hey, the stream ripped the monad off, because it has a lot of the similar operations, such as the monad has a reduce just like the stream does. And it has the filter as well, and it has the map, and it has a few others. I can't remember it off the top of my head. It doesn't have the mutable reductors because that's heresy in functional programming. No. A fluent series is when you directly link functions. You take the return value of one function and then you execute another operation. And then you take the return value of that and execute another operation. The difference is with a stream, you have a data type which is expressing the functions and how they interact. With Fluent, you basically have code that's calling one thing, then another thing, then another thing. So it's not the same thing. Monad is basically a data structure to wire up the input of one function into the output of another function. And this is a really gross simplification, and probably functional programming people would be screaming at me right now, but that's like the basic idea. But yeah, if you play around and get streams and you'll go to monad and you'll say, oh, this is very similar. No, neither monad nor streams are designed for that form of processing. I believe there's something higher order than a monad in functional programming that does do that, but neither monad nor stream have that sort of flow of control. Both of these. Well, the monads and streams are not meant to be like an entire toolbox of tools. They're tools that are made to solve a certain subset of problems very well and without a whole lot of boilerplate code being needed. But if they're the wrong tool, then yeah, you would want to use something else. Yeah, this is definitely not the stream and monads are a hammer and everything's a nail. No, everything's not a nail with this particular tool anyway. There is another functional one, and I wish I could remember the name, because it's, instead of a monad, it's a tree. It's actually a directed acyclic graph, and it can do flow of control and do all kinds of wild stuff. And I can't for the life of me remember it. That might be it. But I wouldn't even go near that thing until you have monad down cold. Because I've read code with that one, and I'm like, wow, you'd almost have to get in the developer's head to understand what this is doing, or at least At least that was my impression. Actually, the stream is easy, especially if you use pure functions, because pure functions, you're always getting the same thing out as what goes in. And sometimes, and this is where the functional references come in, if you really want to unit test stuff, instead of using the Lambda, you'll just use a series of function reference that you can then unit test in JUnit in isolation and then plug them into a Lambda stream. I've actually done that pretty commonly in my own code. It is the easiest way to unit test the steps of a stream, to use function references that way. There are other ways of doing it, but in my opinion, they're overly complicated. Just write a function and plug it into a unit test and be done with it. They are up to speed by necessity. Yes, I got them up to speed. Although, in fairness, some of them came from the JavaScript world, so the whole thing about a Lambda was easy. I just said, oh, they're just like arrow functions, and then from there, I showed them how the stream worked. Indeed. Well, JavaScript has always had closures. It's just that, and arguably Java's had them for a long time too, because the inner class was a closure, but it was so cumbersome that no one would have ever used it that way. In JavaScript, you had to make a new function, which was less cumbersome, so people did use it, but the arrow function and the Lambda sure make it a lot easier. And at least in the case of Java, it's a lot more performant because there are actual optimizations in the compiler and even in the virtual machine that make it more performant than the inner class could have ever hoped to have been. Does Java have yield? There is yield, and you could probably put it in a Lambda. It's probably not a good idea to put it in a stream. I don't really know what that would accomplish, but since you can put any block of code in a Lambda, then it follows that you could put yield in a stream. I don't know why you would do it, though. I mean, yield would just tell the runtime to give the thread to another, to give the runtime to another thread. Yield is not a generator. Oh, well, there is a yield in Java, and it's void, and it doesn't do anything except tell it, hey, give another thread a crack at the processor. So maybe it means something different in C#. Oh, there's a way to do it in Java. You can ask the enumeration its values, turn it into an array list, and then create the stream from the array list. Hopefully in a future version, they'll put the stream right on the enum type. That would be nice. Yep. I've never actually done that. I'll have to remember that if I need to. I've never actually processed the values of enumeration in a stream. I do too. Oh, I'm sure. If there's ever talk on C# streams, I'll probably go to it just out of curiosity. Because I know zilch zero nada about C# streams. Oh, yeah, and see, Java streams have nothing to do with I/O. There actually is an older Java stream that is the composable I/O. So C# are like the old school Java streams. I got it. Yeah, the streams were like I don't know if they were in Java 1, but they were definitely Java 1.2. There's actually a streams package. It's so confusing. There's a stream package that does I/O, and then there's streams, plural, which does which is the thing that may or may not be a monad in Java, depending on who you ask. They always get a big argument about whether it obeys the monad laws or not, and it really doesn't matter. Yep, exactly. When you're going to get work done, it really doesn't matter whether the stream obeys all the monad laws or not. It's monad-like. That's good enough. Yep. That's why on one of the slides I put not to be confused with I/O streams. I do information processing. Basically, people need to put their personnel type information into a system, and we process that type of information. Very DB heavy. I do use ORMs without the relational part, just object mappings, because early on in the project, maybe the technology's matured, I don't know, but the relational part caused more problems than it was worth. And so we've never really gone back. We basically have the Hibernate generator set up to just never generate a relation. No, but I'm going to Google it. Sounds awesome. I bet it will. Honestly, if we're doing anything of significance to our database, we're calling a stored proc anyway. We're not sitting there, at least me personally, I don't sit there and go back and forth with the database and back and forth and back and forth and update. I'll have a stored proc that executes it. It's like at least an order of magnitude, if not orders of magnitude faster. I gotta Google this. Oh, I'll lose this. No, I'm gonna do it on my phone. Vietnam theory of ORMs. I love it. Theory. Coding horror. Ooh. I must have been onto something when I turned off the R part. Because object mapping without the R works pretty nicely. There is a good solution. Just do everything that's complicated in stored procs. Well, I don't know if you can, at least within Java with middle gen, you can make basically a class that tells the generator how to generate code, and it has this method that returns true or false if it should generate a relation, and I just have one that's hard-coded to false. And then there is no R part. It just, as far as the application model, the relations don't exist, and they don't need to. They're enforced by the database. Well, we're moving away from middle gen. We're partly there. I'm talking about Hibernate. In middle gen, you can sort of do it by generating the tables one at a time, which we did. In Hibernate, it's much better. Entire relational. Yeah, that's the whole point, that there is no relational graph in the application. None, zilch, zero, because when we're finding stuff, we use stored procs to find stuff. And we use our web layer to package all the various objects from various tables to update, but we've actually done just fine without the R part. Oh, so we'll hibernate if you don't tell it not to. Maybe C# may allow you to do something similar where you can put a class or a configuration where you get to tell it how you want something generated. The Hibernate one, what it does is it calls your configuration class for each table. So I just have ones that have certain things, like whether it should generate a primary key class that's hard-coded to true, whether it should generate a relation that's hard-coded to false, and then there are a few others that are like that. I love that Vietnam. I love it. Yes, I am in Angular right now. I've actually written an app in Angular. I kind of like it. I don't know if React is any good or not because we did ours in Angular. We use parts of React. We use the observables and things like that. 7. And yes, TypeScript, absolutely. I love TypeScript. I would be in an insane asylum without TypeScript with JavaScript. How did I get out of meeting view? Oh, well, yes, it is. It's very hard to make projects snap together without type safety. I agree. Code for clients or internally? Well, good question. It's for clients because the government and the military are technically clients. However, the application is an internal app. JCPS, as in the big public school system in Louisville. Ah, cool. I can imagine this organization that size probably has plenty to keep you busy. Awesome. Joe Chow. God, I'm trying to remember which one. Was he the one with the weird Java stuff? Oh, okay. Got it. Hello, Joe.